This is my first time using it. So let's consider a normal number, 37, say. In base 10, we can write it 3 times 10 to the 1 plus 7 times 10 to the 0 or something like that. Pi would be 3 times 10 to the 0 plus, 1 times 10 to the negative 1 plus 4 times 10 to the negative 2, so on and so forth. And these kinds of deconstruction, this is what we call decimal, I guess. And the motivation of defining P-Adic numbers is kind of around the fact that we just change the base. And then we also define a notion of size and that sort of stuff. And we see that the P-Adic numbers actually have some nice properties about them. I guess the first thing we should start doing is define the P-Adic numbers, or actually, first of all, ZP, I would say, for this talk is the P-Adic integers instead of the normal cyclic group of order P. For that, we would write something like Z over NZ, like that. So this is the cyclic group of order N. So the first thing I want to do is to define the P-Adic integers, and from the P-Adic integers we can define the P-Adic numbers. Well, the P-Adic numbers kind of we write as QP. So as the notation suggests, QP, the P-Adic numbers, is actually the few fractions of the P-Adic integers. But we shall see that later. So the first thing I would like to define is let's clear everything. The first thing I would like to define is the notion of a inverse limit, and that's how we would talk about P-Adic integers. So a inverse limit is just, well, we first take homomorphisms phi n from a set an to a set an minus 1, and then we can kind of write this in whatever form this is called. So we have a3, and we take the homomorphism a2 into phi 2 into a2, phi 1 into a1, like that, and then this goes on kind of to infinity that way. And we define the inverse limit as the limit to the left of these ANs as kind of a vector type thing. So this thing here inside the product of all the ANs for the thing here. So we're just kind of taking a value, say up here, and then we're passing it down to the next field and so on and so forth. And this will become clear what we're doing if we take kind of each ANs as the ZPs. So we have if we force of habit with notation. So we take this ring here, and then we pass it down to n minus 1, like that, through a homomorphism phi n that we call phi n minus 1, where phi n minus 1 is the normal homomorphism. So we take a value up here, an, and then we pass it down to an mod Pn minus 1. So we define the P-Adic numbers Zp as the inverse limit of these rings here. So why we do that, I actually don't know. It's just kind of a formal thing that is out of Serre, the book. And I guess the next thing I would define is the P-Adic valuation. So the P-Adic, so things at the moment in ZP look something like numbers in the field, these fields, and then we have kind of A to A1, and then they stop at Z over PZ. And this will be in Z over PZ. squared z. So it would look something like a sequence. Say if we have something, a value x in the, say, 3-adics would be something like 7, 2, so 7 would be in z over p cubed, and then so p cubed would be, so this would be mod 9. The next thing we want to do is to mod 3, so we mod this by 3 and we get, sorry, that should be a squared, and then something we kind of mods, we take 7 and then we mod by 3 and then we get 1 from that, and then we kind of reduce that. So then to find kind of a next thing in the number, we want to make sure that it satisfies the homomorphism. So the P-Adic valuation is how we define the notion of size on the thing. So we let a, so for some p in the integers, and we always say p is a prime for this whole thing, we define the valuation vp, a function from z except for 0 onto the real numbers, where vp of a is the index of the first non-zero entry. So what does that mean? Well, if we take a look back at here, so the vp of this thing would be, will be 0, because the index of the first non-zero entry is, well, it's a0. It doesn't exist. But if we had a 0 back here, say, then the valuation would be 1. And we also, for the case 0, we define vp of 0 as plus infinity. And kind of, if we look at what this is actually saying, vp of a, the valuation of a integer, is actually the largest power of p dividing a. So for example, if we take the number, say, 27 inside with p equals 3, then the valuation, the 3-adic valuation of 27 would be, it will be 3. And in the, say, the 3-adic valuation of 18, that would be 2, because 18 is 3 squared times 2, or whatever it is. And then furthermore, we can kind of give some properties about the valuation. So the valuation of the sum of two things is bigger than the minimum of the valuation of the two things we're adding together. And to prove that, we can just look at the powers of the number. So a, if we let a and b in the integers, and then we write a as p to the n a prime and b as p to the m b prime, where a prime is co-prime to p, and it's b prime is also co-prime to p. So that just makes sure that n and m are indeed the largest powers of p inside a and b respectively. And then we can just kind of do a couple of inequalities. So the valuation of a plus b is the valuation of the sum of these two things. And then that's equal to the valuation of, we take, well, without loss of generality, we say that, we can say that m is less than or equal to n. If it's not, then we just swap a and b around. So that means we can ensure that we can always take a factor of p to the m out, and we get p to the n minus m a plus b. And in the valuation of this thing, well, this thing may or may not be co-prime to p, we don't know, but we know for certain that the largest factor of p is at least m, so that means this is bigger or equal to m. and that's the minimum of the valuations of A and B by assumption, because M is less than or equal to N. So so that's just a property of the valuation, and that actually, there's actually something like this, there's a formal definition of what a valuation is, and one of these is we need this as a property, and then that just shows it, the P-Adic valuation is indeed a valuation, but we won't go into that since it's not really a talk about valuations. So the next thing I want to define is the P-Adic norm, and let A be in the P-Adic integers excluding 0. Then we define the P-Adic norm of this A as e to the minus valuation of A. And then if A was 0, or, well, the norm of 0, we just define that to be 0. And in fact, this does define a norm on the P-Adics, because, well, clearly this is always greater or equal to 0. This is equal, and it's equal to 0 if and only if A itself is 0. The fact that this fact here is also obvious because it's an exponential here. And then by the previous thing, by this thing here, we also know we have the triangle inequality. So this thing defines a norm, and then this is how we define the notion of size on the P-Adics. And just a bit of kind of analysis, we can call the P-Adic metric of two values, A comma B, inside the P-Adic. So the metric we define as the distance between A comma B, and we define it in the normal way, A minus B, the norm of A minus B. So that's kind of how we define the notion of size on the P-Adics, and I'm gonna just skip ahead and kind of give us a couple of examples. So, for example, let's go back to what I had earlier. So if we had P equals 3, and we're looking at the 3-adics. So I said before that the P-Adic norm of 27 was 3, because 27 is 3 cubed. And that means that the norm of 27 in the 3-adics would be, it'll be e to the minus valuation, so it'll be e to the minus 3. And then if we look at something like 18 again, so the valuation was 2, if you recall, then the norm of 18 would be e to the minus 2. And actually, in fact, you can probably see that e to the minus 3 is less than e to the minus 2. So that means things with higher powers of p are smaller in the P-Adic norm. So in fact, a large integer, or a large in the normal sense, say 3 to the 20, well, that's a large number, but in the P-Adic norm, well, in the P-Adic kind of space, it's actually quite a small number. It's got norm of e to the negative 20. And that's way smaller than these two things. And then we also will see later on that kind of thing we can, well, smaller numbers also kind of, yeah, appear larger and that sort of stuff. So anything co-prime to 3, say the norm of 2, well, that's e to the negative 0, which is 1. So that's kind of the largest we can get. Okay, right. So so there's a couple of properties. I won't prove them here today because we don't have much time. But we can see that it can be shown that the thing here, the integers modulo p to the n is isomorphic to the thing here, and that's just by exact sequences, and that helps us a bit later on. We can also prove that ZP with the valuation is an integral domain. And we can also show that things like ZP is actually a principal ideal domain, and it is also compact and that sort of stuff. So we can do a lot of analysis and that sort of stuff on it. But I kind of want to go on to the cool theorems and that sort of stuff. So the next thing we obviously want to define is the P-Adic numbers. And the P-Adic numbers, as the notation suggests, is just the quotient ring of, well, quotient field of ZP, the P-Adic integers. Or we can write it like this, up to you. And a number in the P-Adics will look like a fraction, right? And each of these things, x and y, are both in the P-Adic integers, and then we just define the valuation in the natural way. The valuation of VP of A is the difference between the valuation of x and the valuation of y. And note that this doesn't depend on representations of the fraction. That just follows by the fundamental theorem of arithmetic, where we can take or we can just look at kind of the common factors of x and y and how they cancel and how they interact with the valuation. So this just gives a nice extension of the P-Adic integers to the P-Adic numbers. And well, QP is a field, since it's a field of fractions of an integral domain. And in fact, QP is also locally compact and that sort of stuff. It has nice kind of topological and analytical properties. And then we can actually write any, there's a theorem, or actually it's a corollary to a more simple theorem. So for any A inside the P-Adic numbers, this A can be uniquely written in this form, where U is in Z star P. So that just means that that just means that we can write A as P to the something, the valuation of A, times some U that doesn't have any factor of P inside it. And that this representation is always unique. And we can also state that VP of A is bigger than 0 if and only if A is inside the P-Adic integers. So that means the power here is positive if and only if it's in the integers. If it's negative, then it's not in the integers, it's some sort of fraction. So let's just look at a couple of examples. Let's consider the fraction, say, 8/9. Well, we can write that as 2 cubed times 3 to the negative 2. And then VP of 8/9, say let P be say 2, then we look at the cubed here and that will just give us 3. V3 of 8/9, well, we look at negative 2, that gives us negative 2, and say if we have something completely unrelated, say P is 5, then the valuation would just be 1. Then we can easily write the norm of these things as e to the negative 3, then the next thing would be e to the 2, and the next thing would be just e. and then these kind of, you can do a couple of examples yourself. So kind of the first big result I want to talk about is Ostrovsky's theorem, and that kind of says that the P-Adic numbers completes the completes the rational numbers, and it kind of is the only way to complete it apart from the real numbers. So first thing, recall the definition of a absolute value. So an absolute value on some arbitrary field K, and it goes into the positive real numbers, is a function such that one, the absolute value is always positive. Well, actually, it's always positive. It's 0 if and only if x is 0. 2, it satisfies kind of, you can split up the absolute value like this, and then 3, it satisfies the triangle inequality. So obviously, the normal absolute value on the real numbers, say the absolute value of some x is positive x if x is greater than or equal to 0, negative x if x less than 0. This is an absolute value. This is what we'll write as the absolute value with an infinity there. So this is on R. And we'll also, for the sake of notation, and we'll kind of understand why later, we're going to write the real numbers as Q infinity. And this kind of gives us an analogy, since we have the P-Adic kind of norm, and then we also have the real norm, and we have the P-Adics, and then we have kind of the real numbers like that. So the next thing is to define when two absolute values are equivalent. So a absolute value, the first absolute value, and then a second absolute value are on the field are equivalent if there exists a alpha in the positive real numbers such that for all x inside the field we have x, the norm of x is the norm of x under the first absolute value is the norm of the second thing, second absolute value to the power of some number. And note that it doesn't have to be the same alpha. It does have to be the same alpha. Yeah, it does have to be the same alpha for everything. And that's just something from analysis. And in Ostrovsky theorem, the first big and interesting theorem we'll come across today. It states that every non-trivial absolute value on the rational numbers Q is equivalent to either the real absolute value or the P-Adic. So that just means that there are there's an infinite number of ways to complete the rational numbers. There's two classes of ways to do it. Either Q goes to the real numbers, or Q goes to the P-Adic numbers for some P prime. And the proof of this is quite long. I don't think I'll go through this today, but basically it says that there are two cases when kind of a if we take some in the natural numbers, if the norm of n is greater than 1, then the norm corresponds to the real absolute value. And if the norm of natural number was less than or equal to 1, then the norm corresponds to some P-Adic absolute value for some p. And then the proof of this is just a whole case fashion, a bunch of inequalities and that sort of stuff. The next thing, the next cool result, and this one's an actual, I guess, useful result if we want to compute something, and this is Hensel's lemma. And actually, if you've done some sort of applied maths or something, or you would have heard of Newton's method, and the Hensel's lemma is the P-Adic analogy to Newton's method. So first thing I would like to remind you of would be the definition of a, well, we all know what a polynomial is, and we all know what the derivative of a polynomial is. So if we have some polynomial, then the derivative, or the formal derivative, would just be a1 plus 2a2x plus so on and so forth, as you would normally expect. So Hensel's lemma states the following. So if we have a polynomial f of x with coefficients, say c0, c1x plus c2x squared plus so on and so forth, and let the degree be n, and then we take every coefficient, we take the coefficients ci to be inside the P-Adic numbers, or sorry, the P-Adic integers. And if we have a polynomial in, say, if one of the ci's was in the P-Adic numbers, it was a fraction, we just multiply by the greatest common denominator and make the whole thing in the integers. And Hensel's lemma states that there exists a P-Adic integer a in the P-Adic numbers such that f of a, so vanishes, sorry, f vanishes at a, so mod p, and sorry, so it's not there, that it should be supposed, so the condition is that suppose there exists a value in the P-Adic such that f of a is 0 and f prime of a is non-zero. So the derivative is non-zero. Then the result says that there exists a P-Adic integers b such that b is a mod p. So that means b and a are the same mod p, and also f of b equals 0. So basically, Hensel's lemma says that if f has a 0 mod p such that the derivative is non-zero, then there exists a general solution in the P-Adic numbers. And the proof of this is also quite, it's long, but it's also quite straightforward. I guess just follow the steps you would do in the proof of Newton's method, where you just use Taylor's theorem and that sort of stuff. And I'm going to give an example of, so if you look in the notes, there's a proof of that in there. I don't feel like doing it now, but I'm going to give an example of using Heinz's lemma. So first of all, inside the proof of Heinz's lemma, it gives a explicit way of finding a solution to the polynomial. So if we look here, the statement only says, only gives existence, but actually the proof is a constructive proof, so it gives us a method of finding it. So let's take the polynomial x squared minus 10. We wish to consider p equals 3, so we want to look at the 3-adics. Well, clearly, f of 1 is -9, and that's congruent to 0 mod 3. And the derivative is 2, which is not 0 mod 3. So Heinz's lemma tells us that there exists a unique 3-adic integer b such that, so there exists a unique b such that b squared is 10 and b is 1 mod 3. So that means in the, well, this kind of just tells us that 10 has a square root in the 3-adic integers, or 3-adic numbers, I mean. And kind of you can actually write the thing explicitly. I won't do that. I won't. Well, I mean, you can use the formula inside the proof. If you want to write it explicitly, it looks something like the thing here. So it keeps going off to infinity, because recall that we define the P-Adic integers using their, whatever you call it, the inverse limits. So that means the left-hand side can get as large as it wants, but it must always terminate on the right, since we kind of numbers with small powers of p have large absolute values, and we want things to converge, so we terminate stuff on the right and we don't terminate stuff on the left, since those go to 0 anyway. So if you have a large power of p in it, so if we had a large number on the left, that the absolute value of that goes towards 0, since the valuation is large. And then if you look at the notes again, do I have the notes loaded? Yeah. So yeah, so there's a generalized version of Heinz's lemma here, and yeah, the proof of that is similar to the proof of normal Heinz's lemma, and this is useful when we work on problems in general using the Hofmann-Coski theorem, which I'll state a bit later. But yeah, I won't talk about that. If you're interested, just ask me later. So let's go back to here. Yeah, right. So using kind of Heinz's lemma, we can actually prove a lot of stuff, which I won't do because I don't feel like it, and these are long, but we can show that QP is not algebraically closed, and we can also show that we can also easily find the roots of unity of QP, and that QP is not isomorphic to a different QP. Well, it's not isomorphic to QP if the P and Q are different. And then there's a cool feature of the P-Adic numbers, because well, so if we recall an R and we take a series of well, if we take a series and say what shall we call this series? Say some AN, and well, this is A1 plus A2 plus so on and so forth. And if we rearrange the sum, so if we go A2 plus A5 plus whatever we want kind of thing, we rearrange this, we can make the series converge to whatever we like, and that's kind of not very desirable. Or, well, I mean, it's something you wouldn't do anyways, but the cool thing about the P-Adic numbers is that we can actually rearrange a series, and the sequence, the series sum actually always stays the same. That's proposition 3.8 if you look at the notes. There's a proof. It's not long. Well, yeah, it's not long and it's not hard. It just requires a lot of writing, so I won't do that either. Yeah, actually, for that proposition, I think I did it in the last hour of my dissertation being due. So, yeah, it's not a hard proof if you were to kind of have read about it and everything. So now I want to kind of talk about the Hofmann-Coski theorem, which is kind of a big theorem in P-Adic numbers, in the study of P-Adic numbers. So first thing for formalities. First of, we assume the field has for every field we consider, we assume has characteristic not two, so that just means we aren't considering the two-adic integers because weird stuff happens there. As you would know if you've done kind of group theory or algebraic geometry, that sort of stuff, you would know that you never consider the case of characteristic two. Rightio. So we know that kind of if a polynomial f of x has a well, if f of x equals 0 for some x inside the integers, then this means that there exists some say y inside zp, oh sorry, z over pz force of habit for all prime. So that means if it has a solution inside the integers, it has a solution inside the integers modulo p. From what we've looked at before and a bit more theory, we can also say this fact that we can also say something similar where if there is a rational solution, that means there is a solution x, there's a solution y in every P-Adic field. And then kind of that's good, but then what about the converse? Can we go the other way around? Well, we know in general, in this case, it's not true. So for example, let's take the polynomial x squared minus 5x plus 1. Then, well, it's easy to see that this has no roots in modulo 2, because if we reduce the thing modulo 2, we get x squared plus x plus 1 mod 2. So this is, and then neither 0 or 1 is a root in this, so that means there's no root in here. So that's kind of useful where we kind of study the contrapositive, I guess. So if there is no root in here, then there's no root in the integers. And I guess you can do something similar here, where we go, if there's no root in the P-Adic numbers, then there's no root in the rationals. I don't have time. I have a little bit of time. I can do this example. So So if we take this polynomial, three x to the 4 minus 5y squared plus 15x squared minus 25, then I claim that this has no rational solutions. And we can't show it using the normal way. We can't show it. We can't look at the polynomial mod some p, because if we mod it by 3, then it still has a solution. If we mod it by 5, it still has a solution. So those don't give us any information. And modding by any other prime, that wouldn't give us much as well, because we only have factors of 3 and 5. Those are the only things we can get rid of. But what if we consider the 5 adics, the Q5? Well, suppose for contradiction that there exists some xy inside. I guess what would it be inside? It would be Q5 squared. So assume there's a root such that f of x comma y is 0. And then we consider the valuations of, well, I'm just going to rearrange this 5y squared onto the other side. So we have y's on one side, x's on the other side. And then if we consider the valuations of both sides, well, first of all, I'm going to say the valuation of x is a, and the valuation of y is b. So if we take valuations of both sides of this, we should get equality. So the valuation of 5y squared, well, we have 1 power of 5 from the 5, so that gives us a +1. And then we have twice the powers of 5 inside y, so we get 2b plus 1. And then we, on the right-hand side, we get the valuation, the 5-adic valuation of 3x to the 4 plus 15x squared minus 25. This is, well, from the result earlier, this is greater or equal to the minimum of these three things, and then we can easily see that, well, this is a power of 4. The 3 doesn't give us anything, so it'll be 4a. The valuation of this thing would be 2a plus 1, and then the valuation of negative 25 is just 2, since we have 2, I guess, 25 is 5 squared. So we get this thing and this thing, and if we equate them together, well, actually, if you look at this, 2b plus 1 is always odd, and this here, this is always even, I claim, and to see that, we just kind of split this up, make this a piecewise function, and it's always even. So when a is large, the minimum is 2, which is even. When a is small, we always get 4a, which is always even. Hence, we can't get odd equals, we can't get them the same. Wait, sorry, never mind. So if this side is odd, then this side must be odd. But this is always, right, never mind. Forget what I said. So this side must be odd. So that means this side must be odd as well. Well, this is even, so that means the minimum must always be 2a plus 1. But if you, well, you get a contradiction if you consider the different values of a, and that means that this thing, the polynomial f of x comma y, never has a solution inside the 5 adics, and that means it never has a solution in the rationals. Now we want to kind of figure out whether there's a converse to this, and that's where the Hofmann-Coski theorem comes in. So record the definition of a quadratic form. That's just something where the maximum degree is 2, And actually, after change of variables, if you recall stuff from Maths 253 or something, a polynomial you can always write as, so you can always get rid of the cross terms, and you always have a1 x1 squared plus something and a1 xn, something like that. And the Hofmann-Coski theorem states that let f be a non-degenerate quadratic form over the rational numbers, then f has a non-trivial zero. So if there exists some a such that f of a equals 0, if and only if it has a solution in every P-Adic field and also in the real numbers. So if and only if there exists some ai inside qi such that, sorry, I should make those p's, such that f of a p equals 0, where p is prime and p is also infinity. So if and only if it has, record that q infinity is the real number. So that's why we say q infinity, because it's kind of a natural thing. It's the, I guess, largest P-Adic field, or whatever you want to call it. I don't know. So actually, you might think, well, we have one, at the beginning, we have one equation, f, inside the rationals. But then the Hofmann-Coski theorem kind of gives us an infinite number of equations. So we have f in R, we have f inside, say, Q2, f inside Q3, and so on and so forth, Q5, Q7. And that there's an infinite number of equations to check. But actually, it's much more easier to check things in the P-Adics than inside the rational. And well, and it's super easy to check whether something has a solution inside the real numbers. So so I gave an example inside here. So if we consider, right. So if we consider the polynomial in 3 variables, x squared plus 3y squared minus 7z squared, whether this has solutions inside the rationals, well, obviously it does. Just by guess and check, we can see that 2 and 1 is a solution. But then we can also use the Hofmann-Coski theorem to prove it. So so we have to check kind of an infinite number of cases, but then we can break these, well, we can group these cases into classes. So in the real numbers, obviously it has a solution, right? Because we set, well, it's always easy to find a solution inside the real numbers if there exists one. So we just set 1 to be 0, we set this one to be 1, and then we set the thing to be whatever we need it to be. And actually, you can show that, say, in 3 variables, it also always has a solution inside the real numbers if and only if the signs in front of these are never all the same. And that just ensures you don't get complex numbers and that sort of stuff. In the next case we want to check is QP for P not 2, 3, or 7. And the reason why we do that is if we look back at here, well, first of all, 2 is a special case since that's a characteristic 2 field. So we always have to have that as a special case. 3 is special because we have a factor of 3 there. 7 is special because we have the 7 there. Every other prime number we can easily solve using Hender's lemma. And I won't do that here now in the interest of time. The next thing would obviously be to consider Q2. And the reason why we can't use Hender's lemma for, I did not know I can do that. The reason why we can't use Hender's lemma for Q2 is because when we take when we differentiate the thing, we get 2x plus 6y squared minus 14z. And note that the square always comes out the front, and that means the thing always, the derivative always vanishes, and we can't use Hender's lemma. But actually we can use the extended Hender's lemma I talked about before. And it's not hard to check that indeed there is a root in Q2. And then similarly, we can use Hender's lemma for Q3 and Q7 to show it has a root. Those are just one or two lines of working. And then kind of by breaking down this problem into kind of, I guess, 4 cases, R, which is super easy, QP, which uses Hender's lemma, where P is not special, and then we have the 2 adics and then the other ones. So we split it up into 4 cases, and then that's how we can show that a polynomial always has, well, whether it has a root in the rationals or not. And a lot of the time, it's not very easy to check whether a polynomial has solutions. I mean, this time it was easy to see 2 on 1 was a solution, but normally we get some kind of really big numbers or that sort of stuff that we can't check by hand easily, and that's when Hofmann-Coski theorem comes in, because actually all this working using Hender's lemma we can technically use by hand. We can do by hand. We don't have to use a calculator or a computer or anything, and that's why Hender's lemma is so useful, and that's why Hofmann-Coski theorem is such a big result in the study of P-Adic numbers. And that is me for today. Thanks. Any questions?
Thanks, that was good, I think.
I hope it made more sense. I feel like I'm more confident talking about P-Adic numbers than elliptic curves, maybe because I spent a whole year looking at them.
Yeah. It was good. I think I had one question. Wait, I need to look at the notes. Oh wait, where are the notes?
There are a lot of typos in the notes, I realized.
That's okay. Chat. Oh, here. Oh yeah, like it's kind of, I'm a little bit confused. Like in Hensel's lemma, like
Yep.
when you say, so you're saying there's a P-Adic integer, right? Like A and ZP.
Mm-hmm.
And then you have
Yep.
a polynomial. So when you say that f of A is congruent to 0 mod P, do you mean, because A is not an integer, right? It's like in the product of, it's like this direct limit. So how do you evaluate that in a polynomial?
All right, yeah. I don't think I made it clear this time, but we can actually, I have it written here somewhere. We can actually identify everything in the limit to things inside the normal rational numbers, where it was this corollary here.
Oh, everything can be written as.
Yeah, which basically says we can identify kind of, I guess we can identify as a corollary to this corollary. I think I have written somewhere, not in these notes, but we can kind of write out every rational number as something inside the what do you call it, the P-Adics, and then there's actually more numbers because the thing doesn't terminate from the left. So terminate on the left. So if I scroll down to this note here, somewhere here, oh, 1.7 is it? Right here. So we can kind of inductively define. Do I have a pointer here? Right. So I've written here. So we have something in here, right? This is the inverse limit thing.
Mm-hmm.
And then we can define these numbers here, b-ins, and then we can kind of add them up. So we get something, we get this equation. So we get our original number a as the sum of these things. So it'll be some coefficient b1 plus, sorry, that might be a 0, plus b1 times p plus b2 p squared plus so on and so forth. And so you can kind of identify the sequence here with a sum here, and in this sum you can write out as some number you would normally do, something like this, but it doesn't terminate on the left, so it could be very large in the real sense, I guess. So that's
right,
why
this is just decimal now, right? Like how you would expand a decimal. Okay, I get you.
Oh, well,
right, so
then
that makes sense.
This presentation is like, I guess, if we were in base 2, if the two adics, it will be in binary, I guess you can say. So this would look something like a binary number and that sort of stuff.
Yep, I got you. No, that makes sense. Now, because now you can evaluate it just the same as you always would.
Yeah, and I guess that's not what I want to do. How do I get rid of annotations?
Control Z.
Yeah, so you can kind of identify, and then I did a little comment about what we call the P-Adic expansion, but the definition varies where it depends where you look and that sort of stuff. But yeah, so basically, this sequence here is the first value is in Z mod P, the second value is in Z mod P squared, the third value is Z, so A3 is in Z mod P cubed, and so on and so forth. And as you can see, the numbers actually get bigger and bigger. And then the final value A is something. Can I get my pen back out? So A1 would look something, well, how do I say it? So A1 is there, but as the first thing, but then the second thing is A2, but A2 actually is something plus A1, if you get what I'm saying. So it's some value B times P plus A1. Since we at the beginning the inverse limit thing, we wanted A2 to be A1. Sorry, the other way around. We want A1 to be A2 mod P. So that means A2 has to look like this. Some BP plus A1. A3 has to look like some CP squared plus BP plus A1. And then you can see that this is kind of a, I guess, expansion-based P. And that's another way to see why we can do what we did in Henz's lemma, where we can substitute things into a polynomial and do everything there, yeah.
All right, I gotcha. Yeah, that makes sense.
Yeah, it took me like a good month or 2 months to get my head around what the P-Adic number actually was. So, yeah.
Nice.
Yeah, it's an interesting topic.
Yeah, and the reason why I wanted to do this is, well, it's not, we don't directly need it in the elliptic curve stuff, but some of the proof requires the P-Adic numbers, and it helps a lot if you know what a P-Adic number is before approaching the proofs. I mean, you could just look at the definition and it works out, but